Thank you. Well, hello everyone. My name is Mario, and I want to make sure you're in the right room. This is not the pattern matching talk, okay? That's in another room. Surprised to see many people here. You still have time to go to the other one. As I was saying, my name is Mario. I work at Bloomberg, and I want to speak today about basically how to explore some Linux features and concepts from Python. The talk could have been just named that, but it's all about the clickbait, right? So after the talk, I'm going to be around. I'm one of these people that love to get stopped in the hallway and chat about anything. There are a lot of topics you can speak with me about. That doesn't have to be necessarily Python, but yeah, hopefully we'll get to meet and share some time together. So as I was saying, we're going to speak about Linux and Python, and we'll see some basic Linux concepts, hopefully through APIs that you already know. The objective of this talk is that you will get to hopefully know a little bit more of Linux through an environment that you're comfortable with. I think we don't have time for questions at the end, but I'll be at the hallway. Okay, so first of all, Linux or Python. You might be wondering, what does CPython build against? There is, I've put here 2 URLs that you can check that will help you out figure out whether the platform you're working on is supported at Python. On the second link, there's a pep that defines what that supported means. There are situations where a release may be blocked based on issues in that platform, and there are some others where it is kind of like most best effort. There is also the Python buildbots, where it's basically the farm that's building CPython against multiple platforms every day. There is even a watch with a really cool shield. It's kind of like a really slick Drup. You have some people that belong to that here in the talk. But basically, there is people that are making sure that CPython continues to build and to run in multiple platforms whenever there's any whenever there's a new change that's made in the source code. Additionally, you should be aware that CPython release managers only release pre-built interpreters for macOS and Windows. And what that means is that if you're using a CPython in Linux, in any of its distribution, you are basically using something that's built from source. You will need, everything's built from source, but you'll need to build it on your own. Or in some cases, if, for example, you're using in Ubuntu or something like that, there will be some package manager that does that for you. But it's not the Python release managers that are doing that. It's some other third party. So getting into the meat, I'm going to speak through multiple modules that allow you to interact with APIs that are, at the end, providing you services that belong to the OS. And before we start into that, there's something I'd like to tell you, because I find, I work with a lot of Python developers, and sometimes I find that people don't know about many of the modules that are part of the standard library. And we're proud to say that our language comes with batteries included, but we never get to know about all the batteries that include. So here I'm basically listing some of the modules that allow you to interact with the OS, and I'm sure that many people here in the audience have not seen some of them. Some, a module that, for example, I see many people don't know about, and it's, in my opinion, quite handy, is file CMP. That basically allows you to compare if 2 files are equal, or even compare to directories. It's super cool, and I'm sure that many of you have written that code on your own to compare to directories of files, isn't it? So if you have the time after this talk or after PyCon or whatever you can, there's a page in the CPython documentation that lists all the modules in the standard library. Just go through it. I'm sure that you'll learn some new cool module. So we can speak about Linux and Python without speaking about processes. So a really brief introduction. When we're writing a program, all we're doing is basically creating instructions, right? And then those instructions define a program when it's in disk, and you're going to move it into memory, and that creates a process in some way. The process is made of those instructions that we wrote together with some state. There is some memory around it. If you have no experience with it, I recommend that you read some information around the memory layout of a process. I promise you're going to be fascinated. And basically, once you have that in memory, the OS, through the scheduler, will prioritize what instructions are being executed. And that's cool, but how do we create a process in Python, right? So if you haven't seen it before, oh no, the slides are cut. Is there the video, the media people? Is there any way I can like make don't worry. There is a part here in the corner that is going to put on all the slides. I'll publish the slides afterwards. But there is a man command for each of the slides that I'm putting that allows you to go deeper if you want. But I'll just say that that's a pity. So well, fork. Through the OS model, you will be able to run the syscall fork. And what that allows you to do is basically get the current program and create a clone on its own. And that's going to be a child process. This is kind of like the way to create new processes on Linux. You can see that what the API allows you is you call os.fork, and that's going to give you a return code. The return code is going to be 0 in the case of the child, and it's going to be the PID of the parent, the PID of the child in the case of the parent. This is a really handy way to just allow you to run some code in parallel, right? Here you can see how, in this example, we are basically starting a program, right? Then we're calling fork, and those two things are going to be executed in parallel. The child process is going to run the first section of the if, and the parent process is going to run the second part. There is, when I say that when you run fork, the process is duplicated, you might be thinking that, wow, that has to be really expensive, right? And there are many optimizations to make sure that that's not the case. A good example is that, for example, in Linux, there's a concept what's called copy and write. And what that means is that when you're actually forking, you are not copying the whole thing. You are only going to start to copy that part of memory when you modify them, which is really handy if you think about, for example, these functions and all the code that are there, which is not going to be changed. Something that I also wanted to mention here, and which you can find in the man page if you read that, and I really recommend that you run man fork if you ever have to interact with any of this, is that threads are not copied. When you run fork, only the thread that's executing that is going to be the one that's going to be cloned. Again, don't be afraid of the Linux manual. I promise you, it's really nice and easy to read, especially like when you know what the thing is doing. So it's a pity that we cannot see it here in the slides, but there at the top it says man fork. The second thing I want to speak about, you can speak about fork without exec, is the exec API. This is going to allow you to interact. Well, there are multiple functions you can find in the OS documentation of Python, the different functions that allows you to interact with exec in different ways, because you might want to pass different, basically the API just changes how you can pass parameters and some other things. So for example, where the path environment variable is going to be used to find the command. But basically what this is going to do is it's going to replace the current process with the one that you pass it here. So here we're just saying like, this program is just importing OS, and then it's saying, okay, replace myself with this new program. And that's going to execute Python 3.9, and it's going to execute that. You can realize that line number 6 is never going to be executed, because you're replacing the whole program, and therefore the instructions of the previous program that no longer exist in that process. At the top there, you can see a new man reference, which is man exec. Okay, something else that might be handy when you are doing fork and exec is that you can register at fork handlers. What this allows you to do is to execute code before you fork or after you fork, and you can customize that both in the parent and in the child. Python allows you to do this really nicely through this OS register at fork. And you can basically pass function there with what you want to execute. Okay, so you might be wondering, okay, Mario, I've never used any of this. Why are you speaking to me about it? Well, have you used subprocess? If you have ever used a process to run anything like this is a code example taken from the subprocess documentation, you are indeed using this. This is the source code behind subprocess, so you can see there. I'm not lying to you. And here is basically doing fork and exec. Something similar to how I say, go and read the different modules that they have in the standard library. There are some modules that are really easy to read and understand what's going on. So I would encourage you as well to go and read the source code of some modules, because then you can understand what's actually happening behind. In this case, indeed, it's just calling fork and exec. And you can see here how it's the same structure that we saw before, where it's just calling fork, getting the PID of the child, right? And here it's checking if the PID is 0, that means that we are in the child. So it's just it means that we are in the parent, so we are just returning. Otherwise, here you have the code for the child. You can see here again the code to the after fork in the child. There is also another section in the code that does the after fork of the parent, but I didn't include it in this slide. Similar to how subprocess just do fork and exec, multiprocessing does something really similar. So believe it or not, you have been using this all the time, and not only in Python, of course. Some more things. If we start to speak about files, something I love also to show some people is how you can just, you probably know that your process is always writing to standard output, right? And it's reading from standard in. Those are just normal files. They are really not text files, but those are files that you can even open on your own. Here you can see how, for example, you can just open std out and append to it and read from std in. Something to mention here that I know catches some people is you can see here how we write hello PyCon at Salt Lake City, but only the first line is actually printed before we reread std in. If you wonder why that's happening, in the sense of like, why do we see hello Python, we have to press enter, and then the other line appears, when in the code we can see that it's writing twice to std out and then reading from std in. That's because the output is being buffered. I'm sure that many of you love to live cowboy lives and have removed your USB stick in Windows without extracting the device, but that's actually the reason why it's happening, and that's because the Python or the OS, depending, there are multiple layers, will be buffering the output that you write to a file or to a media or anything like that, so you need to make sure that those are buffered before you close. If you want to go a little bit further and see what's actually std out, because you might be wondering, hey, if this is just a file, how come that I can have multiple processes writing to it and they are not colliding, right? I can have multiple terminal screens and they are not interacting with each other. How does this work? So what's actually happening is that std out and std error just point to this like proc self. If you haven't ever walked a little bit through proc, I encourage you to do it as well. It's, you can find a lot of information about the process there. And what's actually happening is that's basically just pointing to a file descriptor of your process. And that's actually, and then I think I have time, and that's actually, I'm gonna show you what actually happens there. And that then is pointing to your terminal. So for example, here, if you see proc self live demo, woo, FD1, so that's actually just a symlink to my terminal. You can see here if I run tty, that matches. And what that means is that basically std out is being pointed to that file descriptor, and then that file descriptor is pointed to my terminal. And this is as fun as you can just take this and write things here. You can write hello PyCon from here. And that totally works. It's just the file. You can even write from a different terminal. And that will work. And of course, you can do exactly the same thing from PyCon. You can see it's here. You can even cut it, like you can even read from it if you want, and then fun things start to happen. Like for example, if you write here, both of them are running, and you'll see it in both places. It's, at the end, the API you're working with is just a file descriptor, so you can just work with it as with any other file descriptor. Really cool stuff. You can, yeah, let's continue because I'm actually running out of time. Similar to how you can open and read files, you can also read about the metadata from Python. There's the stat command in Linux, and you have the stat module in Python that allows you to read all of that. OK, how am I doing with time? OK. So next thing is the locale module. Again, you can read man set locale, and that will allow you to learn a little bit more on the Linux man pages about how the locale works. But this allows you to handle all kind of like cultural specificities about your code. Here I'm putting an example of how you, for example, can use locale to parse that string 43,210 into a float, and you can see that you get different results whether you're using the US locale or the Spanish locales. All programs start with what's called like the legacy C locale. But you can change that once you start by changing the locale here. Probably when you are working with like locale-specific programs, you're using more high-level modules. But it's always good to know what's behind the hoods. And this basically what allows you is to read that information from the OS. If you wanted to add more locales, what you need to do is basically install into your OS some language pack, and that will give you that. Okay, so time. This is a topic I love. If you might be wondering, what's so hard about time? Why do I need the OS to give time to give me the time? Well, the thing is, time is not. Hopefully, this is not new to you, but time is a complex concept to. It's just hard to know what time is this. How crazy it sounds. But the thing is, like in Python, the time is being provided by the OS, and the OS actually works with some hardware clock, which is just using quartz, because that provides that gives you something that gives you a periodic event that you can check, and then your PC is going to check, is going to be able to track how seconds pass by using quartz, and then your OS will be able to read that and will combine that with the time from other PCs, which is being given to you via NTP. At the end, the time is just given to you, is actually being provided by some atomic clocks that you don't have to worry about. But it's good to know that whenever you are asking Python for what time is it, all this is happening. And the reason why I'm saying that is because you might start to build some assumptions around it that you should know. Like, for example, that the time is monotonic and ascending. So that's something you can actually not rely on time. So yeah, like this basically allows us to call to the OS and get the timer that it is. And you might be wondering, yeah, but I never use time.time, I use datetime. Well, if you read the code, it's actually the same thing. All time in Python is actually being provided by the OS by just calling time.time. Here's the underscore time, which is the extension that's actually calling them to the OS. You cannot see the man pages here, but here actually it says man and TPD, and it allows you to know how this protocol that synchronizes your time with other PCs work. Because probably many of you here will have a watch, and it's important to realize that your watch will have a different time from my watch. And even if we were to synchronize them right now, after a day or a month or a year, because your watch is probably based on quartz or it's mechanical, it will lose synchronization with each other. And you need to synchronize them from time to time to make sure that you are following the same time. So you get all of this for free in Python because it's just asking the OS to give it the time. And in case you wonder, because you have seen this like YouTube channel, Veritasium, call like, oh, so how can I handle leap seconds? Well, the thing is like the OS is giving you the time in what's called Unix time, and does not include leap seconds. So if the OS does not know about leap seconds, Python cannot know about leap seconds. Okay, so let's go with signals. So signals are just a software interrupt to notify a process of an important event. There are many events that your process might want to know about, and the OS can pass that to them. You can also just call kill and basically pass a signal to your program. There are usually signals that you can customize yourself, and then there are signals to tell the process to interrupt itself, or there's also a signal that surprised many people, which is the SIG pipe. What that means is that you saw how before we saw, like there's std out, std error, and std in. When in Linux, when you have a command and then you put like the pipe symbol and another command, what actually happening there is that the OS is mapping the std out of your first command to the std in to the first one. So if one of the there's no file there really, right? So what's happening is that when one of those processes die, the pipe is broken because one end is not connected anymore. So that's the OS is going to notify you via that pipe broken signal. Something where you might have seen signal as well if you're running web applications, a really common practice, is to basically handle the SIG interrupt as a way to have a way to tell the process like, hey, I want you to stop because I'm going to restart the machine or whatever. So you can customize what to do with SIGINT and basically clean up your process before exiting. And if they don't exit, then you can just run SIG kill, which no one can overwrite, and it will just kill your process in a nice way. And how is all of this handled in Python? Well, you have the signal module, and here you have an example of how to register a signal. This might cause you a nightmare because you might have realized that now any instruction in your Python program can raise any kind of exception. Please don't start to capture zero division errors around time.sleep, okay? So here you can see how to register a handler for any signal. And something to be aware is how does Python handle those signals, right? Because signals are done on a lower level. So what's actually happening is that Python will always pass those signals and call the signal handlers in the main thread. And the same way that signals are handled in the main thread, signal needs to be registered in the main thread. You cannot register a signal in any other thread. Something that Python will do by default for you is translate sigint to a keyboard interrupt exception and sigpipe to a broken pipe error exception. If for whatever reason you wanted to override segfault and some other signals, that won't work as you expect in Python, because at the end they're going to be passed again to the C level, and your program will not behave you probably expect. So you have another module in the standard library called fault handler that will allow you to do that. Okay, so name pipes. I don't know why I love this. They are a really simple way to have inter-process communication. What this allows you to do is you can have a file where you can have where you can have two processes connect and pass information from one to another. It's unidirectional, and here you have an example on how to do that. Something to note is that you need to have both sides connected, otherwise they will by default block on it. So that's why here you see some APIs related to how to connect without blocking and things like that. And basically, yeah, you cannot see the man page there, but you can read man FIFO, and you'll get more information about that. If you want to use name pipes, go and read that, because maybe some things that surprise you. Something I like to do when I'm using name pipes as well is on the reader process, I like to have as well like an open file descriptor with the right permission as a way to unblock myself if I have some kind of like multi-threading application. But if you like this, you would love Unix domain sockets. So what this allows you to do is similar. You have kind of like a file that allows you to have two processes communicate with each other, but here you have a bidirectional channel, so that means that you'll need to use send and recv. But this allows you to have basically a communication between two processes, similar to how you can use a socket to communicate with a process in a different host. You can use unidomain socket to communicate with a process in the same host. Something that's amazing about this is that because it's a file, you can control permissions, like who can read and who can write, just with file permissions, which I think it's beautiful. Okay, so if you want to do this and you want to combine it with fork and exec, here we have an example that's kind of like full end-to-end. So here you can see how you can use socket pair, which is another function that you have in the standard library, and that's going to give you basically two variables that you can use to communicate between each other. So here you can see that we call socket pair, and then we have the call to fork, and so now you have to know, okay, so I have now two programs running through this, right? And we can see that in the child, we can use this like child socket to send information to the parent, and the other way around, which is a super easy way to send information from one process to another. And if you wonder what is all of this useful for, that allows you to then create, this is the sponsor slide. This allows you then to create products like Membrane. So if you haven't heard about Membrane, it's a new memory profiler that we built. It's the reason why I'm including here is because if you like to know more about like some Linux fixture, I would really recommend that you read through the source code. It has not only some advanced and beautiful concepts, but it's really well documented. And we have actually got some really cool comments from people about how well and fun is to read the source code. I promise, really. It basically have a look through it. I'm not one of these like fanboys that will just like publish a tool like with flags and T-shirts and everything. Don't trust that kind of people, okay? But if you have the time, I would really recommend that you have a look at it. It's totally objective, okay? And yeah, check it out because it has many concepts that you might like that are related to this presentation as well. And that's all I have.